Biased relay force. Relay consists of the winding, steel core and the plunger. Plunger is made of steel and there is a permanent magnet embedded in the plunger. Permanent magnet pulls the plunger inside, but when the current is switched on, the repelling magnetic force pulls the plunger out. Our task is to calculate force versus time dependency after the relay is energized. The voltage magnitude is 3.5 volts. Winding number of turns is 312. Permanent magnet coercive force is 500 kiloamperes per meter. It seems rather a simple task. We can use Transient Magnetics module to simulate switching process. But hold on, Transient Magnetic Analysis starts from zero initial magnetic field distribution. But in fact, we have permanent magnet here, and initial magnetic field distribution is not zero. Moreover, the steel permeability is non-linear. So to calculate initial magnetic field distribution, we should simulate DC magnetics problem. Then we should pass magnetic field distribution from DC magnetic analysis to transient magnetic analysis to be used as initial magnetic field distribution. So let's run QuickField now. I create new problem. I will start with DC magnetic analysis. So this is relay DC. Next. Problem type is magnetostatics. Geometry model features cylindrical axial symmetry, so the model class is axisymmetric. Length units are millimeters. Finish. On the left you can see problem pane, and on the right you can see geometry model editor window. You can draw geometry model here, or you can import the geometry model from the AutoCAD DXF file. I have the geometry model already prepared. Here is the file, and this is the geometry model. In QuickField, axis of rotation is a horizontal one, so we should place the model symmetric to the axis of rotation and then remove the part located beneath the axis. I switch to the select mode, select the entire geometry and drag. You can also specify the displacement manually. Move selection, displacement 1 mm down. Now let's switch to insert mode and draw the axis. Again switch to select mode and remove objects located beneath the axis. Select them, click delete, yes. Well, we have the relay geometry here, but the magnetic circuit is open, so magnetic field should pass through the air. We should add the air to our model. Again, I will switch to the insert mode and I will draw the half arc. That space around the relay would be the air. We have already decided that one part is steel, other part is the air, but QuickField doesn't know about our decisions. Let's assign labels. Switch to the select mode, click and select the object, open the properties window and type in the label. This is the air. OK. Click to select and hold the control button pressed to select multiple objects. These objects are steel parts. I give them label steel. Okay. This is the permanent magnet. Now let's zoom in. This is the non-magnetic spacer. And this is the winding. Let's zoom in again. Here is the insulation. And between the turns we have the insulation too. Okay, I will select the insulation between the turns. Hold the control button pressed to select multiple objects. Okay, I have selected all the blocks located between the turns of the winding, and now I will assign them label insulation. Now let's check the model statistic. Open Properties, Summary. There are 585 blocks in our model and all the blocks are labeled. So we have missed nothing and can specify physical properties to the labels. All labels are listed in the tree and new labels have the question mark. Double-click the label to edit physical properties. For the air I specify a relative magnetic permittivity of 1. For the insulation, the same 1. For the non-magnetic spacer, a 1. For the winding, I specify a relative magnetic permittivity 1 and nothing more. The winding is not yet energized. Okay. For the permanent magnet, I specify a relative magnetic permittivity of 1.05 and the coercive force magnitude 500,000 amperes per meter. The coercive force direction to the left, so 180 degrees here. Okay. For the steel parts, I specify nonlinear magnetic permeability, BH curve. In fact, I already have the data prepared in the Excel file, so I just select them and copy. Okay. That's all for materials. Next, let's deal with boundary conditions. Far away from our relay, magnetic field fades to 0. So I give the label 0 to the external boundary. And specify 0 magnetic potential. Okay. On the axis of rotation, QuickField assigns proper conditions automatically, so there is no need to assign label to the axis of rotation. The last step is to build the finite element mesh. Just press this button and we can run the analysis. Yes, save all simulation files. Here we can see the magnetic field lines. The magnetic field is generated by the permanent magnet, and we can use the contour tool to check the force I select the plunger, follow to the integrals, mechanical force. You see the force is direct to the left. Indeed, the plunger is pulled inside. So that is the initial magnetic field distribution, the moment of time before the relay was energized. Now we can continue with the transient analysis. Again, I will create new problem. The problem name is relay transient. Next. Problem type is transient magnetics. Model class the same, axisymmetric. Length units are millimeters. To be able to pass the data from one problem to another, both problems should be based on the same geometry model. So here in the geometry model, I click and browse for the geometry model file that was used in the relay DC problem. Here it is. Open. I believe I will use the electric circuit to specify turns connection and the voltage source. So I type in the circuit file name here. Circuit 1. Next. For the transient problem you should specify the integration time. I believe 1 second will be enough for the transient problem to converge, but I do not know which time step to specify. Let's use the automatic time steps. Okay. You see we have the same geometry model, the same labels, but the data file is different, and for the same labels we can specify different properties. In fact, the properties are the same for the majority of materials. For air, relative magnetic permeability is 1, for the insulation the same 1, for the non-magnetic spacer 1, for the magnet 1.05, 500,000 amperes per meter, coercive force direct to the left. For the steel, the same BH curve. And for the winding, I specify a relative magnetic permeability, which is 1 for copper. Electric conductivity 55 megasiemens per meter. In fact, there are many blocks labeled with the winding, and I will specify that these blocks are connected in series. The field source is not specified here because we have the electric circuit in the problem setup. The field source will be specified in the electric circuit. Okay. For the boundary condition, we again specify zero magnetic potential. Now we have finished with the geometry model and the material properties. Let's edit the electric circuit. Okay. In the electric circuit you should place all conducting elements. In our case this is the winding. And here I will add the voltage source and connect the voltage source to the winding with the wire. The voltage source magnitude is 3.5 volts. Okay. Now we have all the data ready for the transient analysis, but we have not specified the link between the problems yet. There is no link yet. Open the transient problem properties, follow to the links tab, choose the data type. I would like to input the magnetic field. Next, browse for the source problem. It is relay DC PBM. Here it is. Open and add the link to the data sources. Okay, the link appeared in the problem tree. Now we can run the analysis. Press solve button Yes, save all simulation files. Transient magnetic problem was simulated in 10 minutes. Let's take a look at the results. Here is the magnetic field distribution at the final moment of time, 1 second. Let's calculate the force. Again, I will select the plunger, switch to the integral calculator, mechanical force. Now you see the Z component of the force is indeed positive, so the plunger is pushed out, but at which moment of time the force has changed direction. You can switch the time layer here and get new magnetic field distribution and the new value of the magnetic force. Or you can take a look at the time plot. Right click and choose the time plot. So this is the mechanical force versus time dependency. You can see initially the force was negative, then short time after the switching on the relay, magnetic force has changed the direction. If you open the legend, you can see that X component of the force has changed direction at about 1.7 milliseconds. You can copy all the data and pictures you get in QuickField. You can copy calculated integral values. You can copy pictures. You can adjust the picture and switch on, for example, the color map of the flux density. You can also get the local values. Just select the point, click it, and here you can see magnetic flux density, magnetic field strength. If you click in the winding, you will also see the electric current density. You can edit the coordinates, and also you can use contours to take a look at the field distribution along some line. For example, I will draw the line here and can see the field distribution along this line on the XY plot. And you can see the field data that used to make this XY plot in the table. Points, coordinates, flux density, components, magnetic field strength components. You can adjust the tabulating step, and you can copy the table, or you can save the table as a text file. And remember, this is the table for some specific moment of time. If you change the moment of time, you will get other data. In this particular problem, we also have the electric circuit. So this is the field simulation part, and we have the electric circuit simulation part. And here you can see how the current in the winding was changing in time. On our website, if you search for the biased relay force, you will find the page of this example. You can find the problem setup data, the solution section, the results, pictures, and you can download the simulation files there.